Hi, everybody. It's 1 o'clock. It's time to begin. I'm Ken Ribbett, president of the American Mathematical Society, and it is really my great honor today to introduce the Colloquium speaker at this year's joint math meetings. It's Professor Avi Wigderson, who is coming to us from the Institute for Advanced Study in Princeton. I'll say very little about him except that he's one of the most celebrated and distinguished computer scientists that we know. He has connection with Berkeley, which is where I'm from because he did his postdoc in Berkeley after completing his doctoral work at Princeton University. Today he's talking about a topic that has a very long description on the slides. It has to do with alternate minimization and scaling algorithms.
Hi, it's working. So yeah, like Ken said, thanks Ken. This is a long title and I'm going to explain everything on the title to you. Before I get there, I have to, being a computer scientist, I have to at least say a few words about the subject I'm in, computational complexity theory and the P versus NP question, which anyway will come up during these lectures. So I always, oops, that's really interesting. So I hope I'm not going to lose lots of letters over there. It should be, okay, you can read P different. I think that something will be wrong with the slides, hopefully not too bad. So I often envy the physicists for having the night sky or any world phenomena to describe their central problems. For us, computer science is a bit difficult, but if you just use your imagination, you can think of every star there as a computational problem. And then the P versus NP can be described very simply. You can think of NP as a galaxy of all the problems that we would like to solve, and the class P of all the problems that we can solve efficiently. And so the question of whether P equals NP is whether we can solve all the problems we want to solve, and computational problems are also scientific or mathematical problems. So it's really a question about the limits of our knowledge. And everybody believes that P is different than NP. That's what we are trying to prove for 80 years about. Back. Yeah. We've been trying to solve it for a long time, and so far unsuccessfully. And so what we've been doing, or what complexity theorists are doing on a daily basis, is just classify computational problems according to their difficulty. You want to? This comes and goes. Yeah. All right. Hopefully that will work. We try to classify them according to the computational difficulty. And the way you do is there are a variety, there are zillions of computational problems of all types. And we try to classify them according to the resources they expand. And the main tool for this, developing algorithms for them, developing as efficient as possible algorithms for them. And what I'm going to do today is focus on just one problem and one algorithm. Before I do that, I want to advertise, if you want to read about computational complexity, a book that I just put out, which is free on my website. You can read a lot about all the things I won't say. So as I said, I'll focus on one problem and one algorithm. The problem I'll talk about is this singularity of symbolic matrices. Sounds very specific. The algorithm I'll talk about is alternate minimization. Also sounds very specific. And what I'll try to convince you, the reason I picked this topic for these lectures is that it's much, much broader and deeper than one might think. It connects and has applications in many areas across math, physics, and computer science. Another reason I picked it is because that's what I've been doing the last few years. And it's growing and developing and very exciting, at least to me, so I hope to excite you all about this as well. So I want to get started to describe the problem and the algorithm to you, and then I'll talk some more about this analysis of this algorithm and what goes onto it, what goes into it, and how it connects with these different areas of math. These connections, as I said, are very broad. You don't have to read everything, but it connects to commutative and to non-commutative algebra. It connects to quantum information theory. It has applications in analysis. And the sources of the problem and some of the tools come naturally from computational complexity and from optimization. So I'll try to make these connections as we go along. Let me start by talking about the problem. And actually, to get to the problem, I'll start with a different problem leading to it. It's a very basic problem in optimization. This is a problem of bipartite matching. So the problem is you have a graph and you want to match the left vertices to the right vertices along edges. So for example, if like me, you have 3 kids and 3 types of candy, you want to give one each, but they don't each like everyone. So this is a solution. There is a way to do it. In this graph, there is no way to do it. This graph does not have a perfect matching. This is one of the oldest problems in combinatorial optimization. It's a combinatorial problem the way I described it, and it has an algebraic formulation. You can simply write the matrix describing the connections between the left and right vertices, putting 1 if there is an edge. And then the question is whether there is a diagonal which consists of all ones, which in algebraic language, what you are asking is whether the permanent of this matrix is positive, where the permanent just sums up the products along all diagonals. So it's just like the determinant, only without the signs. You couldn't have put the determinant there because you might get cancellations, but with the permanent, everything is fine. So that's a problem, and this, as I said, is one of the oldest problems. In fact, this problem was solved long before the class P was defined. It turns out that Jacobi, this is 1890, developed a polynomial time algorithm for this problem, studying systems of differential equations. So mathematicians developed algorithms throughout the ages, and only in the 20th century we started giving these complexity classes names. Anyway, he developed this algorithm, and there's this connection between algebra and combinatorics on the board, but it got better when Edmonds started looking at it, and he understood, as we will see tomorrow when we talk about the permanent some more, that it's a nasty problem, it's a nasty function, and it's much nicer to use determinants. And in order to do that, he suggested the following. Why don't we exchange, instead of every 1 in the matrix, we put a variable special to this entry, xij, and leave the zeros as zeros. And if you make this symbolic matrix, that's a symbolic matrix as I was talking about, if you look at this symbolic matrix, then it turns out that it's in fact very simple to prove that the graph has a perfect matching if and only if the determinant, which is now a polynomial in these variables, does not vanish identically. So we have this alternative algebraic characterization of having a perfect matching using determinants of symbolic matrices. And once Edmonds realized this is like 50 years ago, he asked the obvious generalization. Suppose that you don't have just single variables in these entries, but suppose you have just arbitrary linear forms in the entries of the matrix. So you have this symbolic matrix. Every entry has a linear form in some variables. And consider the determinant of this matrix. It's a polynomial again, right? And he asked the question, can you test whether it's singular, whether the determinant vanishes identically. It's a natural generalization, so he basically asks, this will be the problem that will be most interesting to us, and I'll motivate it in a second. It will remain open, so I invite you all to think about it and help us understand the complexity of this problem. And the question, why should we care? So Edmonds asked whether there's a polynomial time algorithm for this problem. Again, just testing whether the determinant of the symbolic matrix vanishes identically. There's no way to expand out this determinant, right? It's a polynomial in many variables. It will be exponentially long. So the obvious way doesn't work. And a lot of us realize that at least you can do it fast if you allow randomization into the picture. You can simply plug random values to the variables and figure out and then compute the determinant. And with high probability, you'll get what you want. So there is a very simple probabilistic algorithm, but we want this probabilistic polynomial time algorithm, but we want a deterministic one. That's the problem, and the question is why? Well, I must say that it doesn't look like a special problem, but we learned slowly that it's an extremely important problem. One way we learned it is through a result of Valiant that I'll talk about tomorrow more, is that singularity of symbolic matrices captures all algebraic identities, basically all identities algebraists are trying to prove are captured by this simple problem. It's somehow complete, and so it's interesting for this reason. But there is a much stronger reason that was discovered later, around 2000, by Cabanes and Impagliazzo, which is truly amazing. I mean, you should stare at it and try to appreciate what it says. It says that if you find an efficient polynomial time algorithm for this problem, testing singularity of symbolic matrices, then you proved something like, it's in quotes, but you proved something like our major goal in life. P is different than NP. And it's weird that this problem captures this essence of this main problem of computer science, but also look at the implication. The existence of an algorithm implies the non-existence of another algorithm. It implies hardness. The easiness of one problem implies hardness of another. So it's a very interesting and powerful result, and that's, in fact, a way to go about maybe proving P different than NP. So that's the problem we are interested in, testing symbolic determinants, whether they are singular or not. It also comes up in mathematics in various places. I won't dwell into this. I want to talk about the problem that we are going to solve. So we said we are not going to solve this. It remains open, the complexity of this testing symbolic determinants. So let me first say that symbolic matrices are very naturally represented as just the tuples of matrices. So every entry is a linear form, so we can give every variable the matrix coefficient it comes with. So every symbolic matrix is just a tuple of matrices in the field. By the way, this question is interesting over every field, but we will specialize a little later. And we are given this tuple of matrices, and the question we were asking ourselves is whether this, this matrix is singular, the determinant vanishes. So singular where? So if we ask it like this, we ask whether it's singular when the variables commute. We ask whether it's singular whether it's invertible or singular over the rational functions in these variables. And as we said, we don't know the answer. So what we are going to do is, like every good mathematician, just change the problem and try to find another problem we can solve, which will turn out to be at least as interesting. Or I don't know if at least as interesting, but extremely interesting. And this is a question when the change we make is make the variables do not commute. Okay, it's another thing you can consider. And then the first question you should ask or scratch your head, unless you are doing non-commutative algebra, is where are we trying to take the inverse of this matrix? The answer is, of course, in the field of non-commutative field non-commutative rational functions. This is a really weird object, and we'll talk about it tomorrow in more detail, but it's well-defined. And once you try to ask this question, it seems that it's much, much, much harder than the first. In fact, even decidability took work to, to prove. So just the fact that there's a finite algorithm to test this is complicated. And Cohen Rethenauer got an exponential time algorithm. And then it remained open what is the complexity of this problem. And the main result here of some series of papers is that it can be tested in deterministic polynomial time. In this result, it works over Q, or fields of characteristic 0. And in the second, it really does it over every field. So again, automatically, you shouldn't be excited about the fact that the non-commutative singularity of symbolic matrices has a polynomial time algorithm. What I'll try to explain is both what the algorithm looks like and also what is the connection to all these fields in math and physics that I mentioned, because this algorithm solving this problem is both borrowing tools from these other fields, but also solving basic problems in this field. So I'll try to tell you about that in this first lecture, and then I'll go into more detail in the next two lectures. So I'll tell you today about this first algorithm for fields of characteristic 0. And I want to now introduce the algorithm, this alternate minimization algorithm that I promised. It's a very special type of heuristic. And I'll introduce it first on the combinatorial problem of perfect matching, and then I'll turn to explain how it works in the more general problem of singularity of symbolic matrices. So for this, I need to define one more problem, which is equivalent to testing perfect matching. It's not difficult to show, but it looks really, really different. So here's the problem. It was introduced by Sinkhorn. I'll tell you why in a second. It was introduced by Sinkhorn, and it's the following problem. You have a non-negative matrix, and what you are trying to do is try to make it doubly stochastic. That's the problem. What does doubly stochastic mean? It means that the row sums are 1 and the column sums are 1. That's what you want to do. What are you allowed to do in order to make it doubly stochastic? You are allowed to scale. Scale means multiply the rows by constants and multiply the columns by constants, by scalar. So in other words, multiply from the left and from the right by diagonal matrices. And what you want after that is that the matrix you get will be doubly stochastic. So doubly stochastic scaling is just finding if there exists such matrices which make it doubly stochastic by scaling the rows and the columns. So if you think about it, it looks like, well, first of all, a weird problem. It's clearly nonlinear. You seem to have a shot at it. You have 2n degrees of freedom, the scalars, and you have 2n constraints, the equations making it, demanding the double stochasticity. So it looks like you have a fair chance of doing it for some matrices. Of course, you cannot do it for the 0 matrix. So that's the question we are asking, whether it's possible for a given matrix and then finding the scaling factors. And I want to stress that we just will try to make it approximately doubly stochastic, try to make it as close to doubly stochastic as possible. The question is whether we can approach double stochasticity. So why did he ask this question? It turns out this is just a small subset of applications of this problem. It's turns out to be very important. He was interested in it for reasons of numerical analysis, of solving linear systems. It has application in signal processing. And the reason we care about it here is because it captures the perfect matching problem. It turns out that this is possible. Such scaling factors exist if and only if this matrix has a perfect match. The permanent is positive. OK, so how are we going to solve this problem? As I said, it's nonlinear. It looks like it's not convex. It can be convexified. But what Synchron had suggested is the following really beautiful idea. So let's try to do it on an example. Again, we are looking for scalars multiplying rows and columns to make it doubly stochastic. And it looks difficult. But double stochasticity, making row sums 1, maybe column sums 1, at least you have two sets of independent constraints. Any one of them should be easy. So we can try to solve half the problem. Like, let's try to make all the row sums 1. Can you do it? Yeah, everybody can do it. We just, divide the first row by 3 and leave the others alone. So we can just scale the rows. OK, so we scale the rows, and now the rows are fine, but the columns are not. So we can fix the row, we can fix the columns. Let's fix the columns. So let's experiment with this idea. Yeah, if we can scale the columns, and now the column sums are 1, and the row sums are screwed up, so we can scale the rows. And I think you get my drift. We can continue doing it, and you see that somehow this is what it will converge to. So it will alternate. So there will be no convergence. And actually, it's not so surprising that it doesn't. It's given that it's sort of supposedly equivalent to the existence of a perfect matching. This graph does not have a perfect matching. So this algorithm doesn't converge. Let me give a sort of a more formal description of this algorithm. We are just given this non-negative matrix A. The algorithm is this alternate scaling of rows and columns. The scaling is very easy to calculate by how much we should scale every row or every column, these scaling factors. And we just run this algorithm. And the main claim is that this will need all we need to do is just do it for a small amount of time, just a short amount of time to figure out whether it converges or not. Let me just, OK. This idea of you have a complex problem, so you work on different pieces of it which are easy, and you just alternate between them, is the alternate minimization heuristic. It is extremely broad, and I'll show you some more examples towards the end of the talk. But for now, let's do just another example. Here's the other example that I showed you. Here, there's the matrix of a graph with a perfect matching. So hopefully it will converge, and we can just try to scale rows and columns. Let's just do it. You can see that everything off diagonal shrinks, and this converges to this matrix. And that's what we would have hoped. So anyway, it works in those two examples, but it turns out to work in general. And I want to explain what kind of analysis is required for this, because this will be the same analysis we will need to apply in the more serious problem, the real problem. So we run this alternate scaling of rows and columns for about n cubed times, and then we just test whether we are close to being doubly stochastic, whether the row sums and column sums are very close to 1, let's say up to 1 over n. And it turns out that we can say, if the answer is yes, then we say that there is a perfect matching or there is a scaling. In other ways, we say that there isn't. And in order to understand what's going on in this algorithm, or to analyze why does it converge or not converge, what we need is, obviously this algorithm generates a sequence of matrices, and is, sort of a dynamical system. And to understand convergence, we need a good progress measure or potential function. And here, a very convenient one from this paper was actually using the permanent itself as a progress measure. Later, we will need different ones, but why is the permanent good? I'm not going to prove anything, of course, but I'll tell you what there are 3 steps that are really easy in this case in order to prove that convergence is fast. So what does this potential measure has to satisfy? It has to satisfy that it's always bounded, in this case by 1. At every step, it grows non-trivially. So this asterisk means it grows as long as it has room to grow by a factor 1 plus 1 over n. And so the last piece should be that it starts not too low. And in this case, in this simple problem, this is very easy to show, that if the permanent is positive, then it's actually not too small. It's only exponentially small in n, which means that after a polynomial number of steps, it will get to 1 if it gets to 1 at all. And of course, if the permanent started out being 0, then we will not get anywhere. It will stay 0 forever. So this analysis is very simple, and we will see later that the analogous analysis in operator scaling is significantly more complex and brings about these connections that I talked about. So this is the analysis. Here it's simple. And now I want to explain what is the algorithm that solves the more general problem, the problem of non-commutative singularity of symbolic matrices. And the algorithm actually existed for something like 15 years. Only its analysis didn't exist. So this algorithm is the operator scaling algorithm. And it was developed by Gurwitz. So what I want to explain is the leap, this quantum leap. It's a pun, which is intended, which brings about one of the ways in which symbolic matrices arise in other fields, in this case in quantum information theory. So we started with a problem in algebra. We have this input, which is a tuple of matrices, and we want to know whether the symbolic matrix is singular or not over the non-commutative field, whatever it is. And what Gurwitz did is view the same input in a completely different way. It's still a tuple of matrices, but it can be viewed as a completely positive operator. So completely positive operator is a notion from quantum information theory. It is a map that takes matrices to matrices in this way. So it takes a matrix P into the sum of AI, P, AI transpose, given these AIs. It's called completely positive because it takes positive matrices to positive matrices, and the way you should think about it if you are in quantum information theory is that it takes a quantum state to a quantum state. And what kind of question was he asking about, this input? He wanted to solve the original Edmonds problem, the commutative singularity problem. And he realized that it's connected to the following question: the question of whether this operator can decrease the rank of any input, whether it can ever take an input P, a positive matrix P, and reduce its rank. Now, this connection turns out to be incomplete. It holds for, if all the AIs are rank 1, but it doesn't hold in general. And really, the starting point for the progress was, in the last couple of years, was realizing that there's an old result of Kohn, the same one I mentioned before, showing that these two conditions, the rank decrease of a quantum operator and the non-commutative singularity, is the same question. So also by this, you have a complete description of what non-commutative singularity is. You can forget about this strange notion, just think about whether an operator can reduce the rank of any quantum state it takes. And so that's the question he asked, and he also realized that this question is a generalization of matrix scaling in the sense that you can define what a scaled operator is. Like we had the double stochasticity of matrices, there is a double stochasticity of operators. And this is what it is. It's basically that when you apply the operator to the identity, you get the identity. That's like the row stochasticity. And similarly for the columns, you just have to think about the dual operator, just switch the transpose. So there is a notion of scaling. And basically, you can just automatically, without even thinking, just apply the previous algorithm and see what you get. So just pictorially, The only difference is that we have now a tuple of matrices. So we had a positive operator, a positive matrix, now a positive operator. We have a notion of double stochasticity, and among the differences you get when you move between classical and quantum, you move from L1 to L2, you go from vectors to matrices, from diagonal matrices to general linear matrices or invertible matrices. So the only thing that changes is that the action on the left and the right, this becomes a basis change as opposed to scaling by scalars. And the algorithm is here. I will not say much about it except to get to the analysis. So again, there's a notion of scaling. We can multiply by the left and by the right, trying to make the operator row stochastic or column stochastic. It's very easy to calculate, like before, what it takes to move between the two, to scale the rows and scale the columns. And you just alternate it for some polynomial number of times and test whether you are close to satisfying double stochasticity. And as before, convergence tells you whether it's singular or not. And so it's just verbatim copying the same idea as before. And the only question is, how do you analyze, how do you prove that a polynomial number of steps suffices here? And the key, key insight of Gurvitz was to define a notion that replaces the notion of the permanent. And he actually tried quantum permanent, which can be defined, but it didn't work. And the one that works is this notion of capacity that will come up on Friday again.
Avi, what's C?
Some, I don't know, 10. You really care about constants, David. Yeah, so it's some constant. So capacity is the ratio. You look at the ratio between the determinant of what you put in your operator and what you get out. And you look at the infimum over all positive definite matrices. It doesn't have a quantum meaning as far as I know, but it fits perfectly with the analysis that we had before. The same kind of thing works. So first of all, it converges exactly if the capacity is positive. And the analysis looks the same. Capacity is at most 1 in this sequence of matrices, operators you generate. It grows at every step, again, by a simple reason, the AMGM inequality. And the last part that was needed, that didn't exist, and exists in this work from 2 years ago, is that if you start with positive capacity, then actually it's not too small. It's only exponentially small. So a polynomial number of steps will get it to convergence fast. And this is really the crux of the main thing to prove, the main thing that was open in Gurvitz's paper, and the main thing I want to tell you about. Where is this lower bound coming from? I told you that in the case of permanent, it was very simple. It was really an exercise. How can you prove something like that? And so you have to obviously understand what capacity is. Let me tell you. Okay, let me just say that this algorithm solves this polynomial time algorithm that I mentioned for non-commutative singularity. And moreover, capacity may not be obvious. It looks like a complex function, and in fact, a complicated function. In fact, it's non-convex. And the fact that this is a polynomial time algorithm for a non-convex function, whenever you have a polynomial time algorithm for a non-convex function, is a reason to celebrate, because lots of problems we encounter and want to solve are non-convex. So this is one of them, and we'll explore some applications of this to non-convex optimizations on Friday. So I want to talk a little bit about where this is coming from, but first I want to say something about just the sources without giving you any information. And the sources, we saw already one, is the fact that a tuple of matrices has meaning in lots of contexts. And in lots of contexts, it has meanings that are different from each other. And we can borrow intuition from these different fields and use it in the analysis. So we saw already that it can be viewed as a positive operator. In non-commutative algebra, it turns out that it can be viewed as a rational expression over this non-commutative field. In invariant theory, it can be viewed as representative of a certain orbit of some group action. In analysis, we'll see this on Friday, it can be viewed as a description of a certain type of inequality, of the Braskamp-Leib inequality. In optimization, it can be viewed as a description of a linear program of exponential size. In all of these areas, these descriptions also come with computational questions. And because of the algorithm, that's why this problem is so important, because of this algorithm, all these problems have efficient polynomial time algorithms. Now, I told you about this a few minutes ago. I will explain the connections to non-commutative algebra and invariant theory tomorrow, and how this is really a question about proving algebraic identities. That's the title of the talk tomorrow. And I'll tell you on Friday how this is connected to analysis and to optimization. Let me check my time and see how I'm doing. OK. So I want to tell you a little bit about the connection to invariant theory via some recent work that I'll talk more about it tomorrow. And then I want to tell you just cases of alternate minimization that we simply don't understand. We understand quite a bit more than we used to. And this is in the group theoretic context, if you want, that I'll just describe next. And then I want to just describe a few cases of the alternate minimization algorithm, which we don't understand. And that's, so the field is far from understood. OK, so I want to now think about generalizing. We saw two examples of algorithms, and I want to somehow unify and generalize them. And we will also point to something quite interesting that is a question that maybe should not be asked. Where does this scaling come from? I mean, in the two examples I gave you, the problems were to scale something, to scale a matrix or to scale an operator. There were reasons to ask this question, and these problems were solved, so we should be happy. But still, it turns out that the scaling is not is something very generic and would have been discovered even without the applications, just because of mathematics. So this is from just work a few months ago. So the unification is the following. We are going to look at group actions. We saw group actions. Maybe I didn't stress it, and now I will, in the algorithms that I talked about. So we started the goals of these algorithms were to scale either a matrix or an operator. And the algorithms were applying elements of a group, either diagonal matrices or general linear matrices, either on the left or on the right. So we had products of groups. That was how the algorithms work, just applying group actions. And the analysis of this algorithm were based on trying to understand how some potential function was being minimized or maximized. Anyway, the analysis had optimization in it. What I'm going to do now is going to switch the goal and the analysis. I'm going to start from the analysis as a goal. Suppose we wanted to optimize some function, a very natural function, on an orbit of some group action. And in fact, this group that will be a product of linear groups. So that's what we are going to do here. Suppose we have a group which is a product of linear groups, let's say special linear groups. And they are acting on vector spaces, just as usual, just by matrix vector product. So we have a group acting on a vector space, and it's broken up like this. And we are trying to optimize something. Given a vector in this vector space that is being acted on, suppose we want to compute the minimum L2 norm that we can get to by applying some group element from this group product. Again, like with the problems I mentioned before, it may not be obvious why this is interesting. So let me tell you why it's interesting. So this problem is sort of, you are trying to find the lightest vector from the L2 sense among all vectors in the orbit of the initial vector under the group action. Well, in the case that you have just two groups, we saw already, it turns out, it's not obvious, but it turns out to generalize the two problems that we talked about, matrix and operator scaling. But it gets even more interesting as you go up to more groups. It turns out to capture questions in representation theory, like the positivity of Kronecker coefficients. And when you get to arbitrary k, or any k, it captures the quantum entanglement distillation problem in quantum information theory. And there are lots of others that I'm not mentioning here. So this is a really basic question. And the reason it's basic is that it has a meaning in invariant theory. The meaning it has in invariant theory is you look at this optimization problem, you're trying to find the lightest vector, and the main question is whether the lightest vector shrinks to 0 or not. Shrinks to, you can make it arbitrarily small. And you can make it arbitrarily small if and only if the initial vector that was given to you is in what's called the null cone of the group action. That's just what, the definition of being able to push this vector and make it shrink to arbitrarily small. And that's a basic question in invariant theory and in geometric invariant theory. You want to understand it. And that's because it's this question that it appears in the, it has many manifestations in these and other cases. So why should this tell us anything about the scaling? There is no scaling in this problem. There's just an optimization problem over group action. And the reason is the following duality theory of geometric invariant theory. So what I just told you is that this optimization gives a 0 value, if we can push the vector by the group action to being as close to 0 as possible. And the duality theory of, there's a non-commutative duality theory in invariant theory that tells you that when you cannot do that, when can't you push it to 0? When does this optimization stays positive? And it turns out that this happens. There's a notion of, Lagrange conditions that you can write down. It's called the moment map. And you just write them down, and it seems that, it becomes evident that you cannot approach 0 exactly when a certain set of scaling conditions are satisfied. So scaling arises naturally from this optimization problem. And of course, it will not be double stochasticity. If we have k groups, it would be k-way stochasticity. But in any way, it suggests an alternate minimization approach to this. You have k scaling conditions, and you cycle through them, try to satisfy them. And this turns out will get you, will converge or not converge, and you will know exactly whether the vector is in the null cone or whether the optimization value is 0. I will not talk about the analysis of this. Let me skip to telling you just a few examples of this minimization, alternate minimization problem that we cannot understand. So let me recap the idea of alternate minimization that we just saw in action several times. You are trying to solve whatever it means to optimize or to do something with a multivariate function, and trying to find, let's say, the optimum, the minimum of this function simultaneously over all variables seems difficult, but somehow, if you fix all values but one, and you are trying to optimize just on one variable, then it's simple. This at least was the situation in all the cases that we saw. In fact, in the quantum case, it's not just simple, it's also sort of local. If a quantum state is distributed between many players, everyone can change only its own part of the input. So in any case, in both these situations, you can cycle through optimizing one variable at a time. This is the alternate minimization heuristic. And the question is, when does it work? And here are some cases which we don't understand well. Here's actually came up a long time ago by von Neumann, a very basic question. There are two convex sets in very high dimension, and you want to know the distance between them. Okay? So what can you do? This is not a convex problem. So what von Neumann suggested is, well, you know, alternate minimization. I'm not sure he was the earliest one. I think it came up even before. So in this case, it's alternate projection. Just start with any point in any one of the sets, and then start projecting it to the other. And then project again, then project again, and clearly it will do something good. What von Neumann proved is that this always converges, and in the case that the convex sets have some structure, like there are closed subspaces, it will actually converge in polynomial time. But it's an open problem whether it converges fast in general, and having criteria is extremely interesting. That's one problem, which we don't understand. Here's another place where it comes up. It's, again, these things may be familiar to you from, it depends which area you are in. In statistical physics, what's called Gibbs sampling or metropolis algorithm. What is this problem? You have a distribution, again, on two or many parts, and you are trying to sample from it. And sampling from it will be or may be difficult. And again, you do the same we talked about before. Here is more or less alternate, not projection, but conditional sampling. You just repeatedly sample from, according to the conditional distribution, one of the coordinates given the other ones. And you repeatedly do this, and that's an alternate minimization type algorithm. And it turns out that it converges. In fact, it relates very much to the example before of distance between convex sets. But we don't understand the speed of this convergence. And the last example, which I will not say in detail, is Nash equilibrium. You're trying to find, strategies for two players to play that are sort of each is the best response to the other. There's a famous algorithm of Lemke and Howson that just alternates best response. It starts arbitrarily and repeats best response to the previous strategy. And it always converges, but can be exponential time. So a very big open question is whether this problem is in P, whether it has a polynomial time or any faster algorithm. So summarizing, I told you about, so let me just read it. I told you about just one algorithm and one problem, and the kind of interactions that it has with math and physics and other areas. And this is typical. Maybe this variety of areas that happen to interact here is atypical, but almost always it's, it leads to interesting mathematics. We talked about alternate minimization, scaling algorithms, and the problem of singularity of symbolic matrices. And as I mentioned, they are extremely rich in their sort of importance and connections. And more generally, It's sort of strange, and I don't know many examples. The problem we really looked at, the singularity of symbolic matrices, is purely algebraic, and nevertheless, the algorithm, the efficient algorithm we have for it, is analytic. And on the other hand, we have this analytic algorithm, a continuous type algorithm, but the analysis is essentially using tools from algebra. So among many open problems, I told you about the commutative question, and in particular, its implication to something like P different than NP. It's extremely interesting to explore the power of this algorithm to optimization. And you saw from the last examples that we are far from understanding even this very simple heuristic. So tomorrow I'll talk about one part of the analysis and the connections to algebra and to algebraic identities. And on Friday, I will talk about applications of this kind of algorithm to proving inequalities and to optimization. Thank you.
Thank you very much. We actually have time for one or two questions. If people have questions, they can come up to the microphones and address questions to the speaker. And if not, we will just allow the lecture series to continue tomorrow and Friday. So let's thank the speaker again for a great talk.